We are going to discuss analog communication, and in this particular lecture series we will try to understand analog communication in a brief fashion so that uh, you will be able to understand the topic easily, and I will try to avoid the rigorous mathematical analysis so that it will be easier for you. This is just a preliminary lecture series. Well, communication is the process by which we can transfer some information from one point to another point. And that communication system may be of different type, like multicast, broadcast, etc. We will discuss, or we will try to discuss later on. Now let us try to understand the basic block diagram of any communication system. The basic blocks are like this: one input transducer, a transmitter, there will be some channel, then receiver, and finally the output transducer. And in the channel there may be some noise or distortion, and that will be added in the channel in this way. So according to the block, the noise and distortion are added in the channel, and most of the noise is actually coming from the channel. Now let us try to understand the functions of each block. The input message is assumed to be a voice signal for this case. First of all, you have to transfer this voice signal, which is acoustic signal or the sound signal or sound wave. We have to convert this sound wave into equivalent electrical signal, and for that we need this input transducer. It is same as that of a microphone, you can assume it. So microphone will convert an acoustic signal into electrical signal. So this is actually the input signal. The electrical signal is our actual input signal that is coming to the transmitter. Now transmitter has got several functions. One of the major function of the transmitter is to manipulate this input signal. Manipulation means it will filter out the out of band signals. That means if there exists some other frequency components or undesired frequency components, it should eliminate that particular those components. Next, one of the major function of the transmitter is the modulation. We will discuss modulation later on. After modulation, the modulated signal may have some extra frequency components, and those frequency components must be eliminated. So that is done with the help of some band pass filter. That is also a function of this transmitter. And then the filtered signal, modulated signal, must be amplified so that can travel through the channel. Not only that, this transmitter must be selected in such a fashion that the transmitted signal must be compatible to the channel, because any channel cannot support any signal. For example, if the channel is optical fiber, then we cannot transfer signal of frequency say 1 megahertz or 2 megahertz. We have to convert this signal into optical domain. So likewise, that is the job of transmitter. So transmitter will make the signal compatible to the channel. Now the function of channel is to transfer the signal, modulated signal, from the source to the destination with minimum amount of attenuation and distortion or error. The channel has got certain properties. Each channel, we have different type of channels. Like we may have air medium, that is also a channel. We can have optical fiber, we can have copper cable, etc. Now in the channel, distortion and noise may added with the signal. Now noise is, we will discuss noise later on. Noise is some undesired signal added with the original signal, and distortion is basically coming from the problem of the channel. This is the property of the channel. Distortion is the property of the channel. Actually what happens, in the channel all the frequency components may not travel the same velocity. So when they will appear at the receiver, they should appear at the receiver at the same time. But as the velocity is frequency dependent in the channel, so the signals, different component of the signal will appear at the receiver at different time, and that will produce some change in wave shape of the original signal. That is what we call distortion, and that is a property of the channel. We can have some measures to reduce this effect of distortion, but for the time being, we assume that the signal will be little bit distorted because of this noise and distortion in the channel. Now at the end of this channel, or at the start of this receiver, the signal will be very weak, obviously, because the channel may be of thousands of kilometers of length. So obviously the signal will be weak. Now the receiver, what the function of receiver? Receiver, first of all, when it receives the original signal coming from the channel, it is receiving weak signal. So first of all, the receiver must amplify it. Not only that, receiver must remove any sort of undesired out of band signals. That means receiver must filter out the received signal. So these are two major jobs that should be performed by the receiver. One is the filtering, another is the amplification of the incoming signal. Then another job of the receiver is, transmitter has modulated the signal and the receiver must demodulate it. So demodulation is another job of the receiver. Now the demodulated output may be very weak. Also it may require some filtering. So filtering of demodulated signal and the amplification of the demodulated signal is another job of the receiver. These are the functions of the receiver. Now at the output of the receiver, we should get the original message signal or the replica of this message signal here. Replica of the message signal, electrical message signal, right here. So here we have the electrical message signal. Now electrical message signal must be converted into the sound wave, acoustic wave. So we need an output transducer that will convert an electrical signal into an acoustic signal. This is done with the help of a speaker, or this can be done with the help of a speaker. So this is the function of this transducer. Now we need to understand the process called modulation. Generally, baseband signal, the original message signal, cannot be transmitted directly to the destination. Why we need this modulation, we will discuss later on. Now a signal may consist of three parameters. One is amplitude, another is phase, another is the frequency. These are the parameters of a signal. So what we do, we actually change any one of the parameter, either amplitude or phase or frequency of a signal. We call that signal as carrier signal, depending on the variation of the baseband signal. And this process is called the modulation. That means modulation is the process by which we change the parameter, amplitude, phase or frequency of carrier signal depending on the variation of another signal called the original message signal or the baseband signal. Sometimes it is also called the modulating signal. Okay. Why do we need this modulation? So first, the efficient radiation. For efficient radiation, the antenna size is of the order of lambda by 2, where lambda is the wavelength. Now if we consider the voice frequency is up to say few tens of kilohertz, 20 kilohertz is the maximum limit. So if we consider that tens of kilohertz, then the corresponding wavelength would be of the order of few hundred kilometer. That means if I want to transmit the voice signal, we require an antenna of length half of the hundreds of kilometer. That means of the order of 50 kilometer or more than that. Now antenna size of 50 kilometer is an absurd idea. That means we have to change the frequency from voice frequency, that means few tens of kilohertz, to higher frequency levels, so that the antenna size gets reduced. So this is the first requirement of the modulation. Second need is the simultaneous transmission of several signals. If I want to transmit number of signals, number of voice signals, all the voice signals are in the same frequency domain, tens of kilohertz. So there is a chance of overlapping or superposition. So what we can do, we can allot different carrier frequencies for different signals, so that they will never interfere. So they can be transmitted through the same channel and they can be recovered back. That means simultaneous transmission is possible if we have modulation. Now if we transmit the signal directly, then there is a chance of excessive amount of noise introduction in the signal. Now there are several techniques of modulation that changes the signal to, that is able to change the signal to noise ratio. That means we can improve signal to noise ratio, so the signal quality at the receiver would be better. That is possible using modulation. We will discuss this later on. Improvement of signal to noise ratio, we will discuss it later on if time permits. Next is the efficient use of bandwidth. If we have purchased some bandwidth, then we must use this bandwidth efficiently. Now different modulation has got different bandwidth. We will discuss it later on. So if we have purchased say 200 kilohertz of bandwidth, we must use this 200 kilohertz bandwidth efficiently. That means we must utilize it properly, and that is possible if we have a specific type of modulation, if we have selected specific type of modulation scheme. So these are the need for modulation, but there are some fundamental limitations of communication system, that is the noise limitation, bandwidth limitation, and the equipment limitations. And I am not going to discuss these things in details, because that will make this whole lecture series very bulky. So we are avoiding to explain these things. Now let us recapitulate something that we have already discussed, or that you have already learned in your previous classes in signal and system. So first of all, what is the meaning of signal? Well, signal is any, in signal in means we are trying to mention that here we are using electrical communication. So signal implies it is an electrical signal. So we define this electrical signal in this way: the variation of electric current or voltage is the signal. So if there is no variation, we cannot call that particular entity as signal. Now signal may be classified depending on the various aspects. it can be classified as periodic signal and aperiodic signal. Periodic signal means a signal that repeats itself after a certain period of time. That means if a signal is represented by GT, then it should be repeated itself, should repeat itself after a certain time of say t0. This is what we call the periodic signal. And for aperiodic signal, the signal will not get repeated. So any time bound signal is an example of aperiodic signal. Now signal may be divided or classified by some other means also, like depending on its voltage value, the condition of its amplitude, we can divide this signal as analog and digital. Now what is the meaning of analog signal? If the amplitude parameter of a signal can take any value within a certain range, it will be treated as analog signal. For example, this signal within a certain range of plus MP to minus MP, this signal is taking any value. It may be 0.1, it may be 0.2, it may be 0.3, etc. It can take any value. It can take 0.001, it can take 0.002, etc. That means within a limit of plus MP to minus MP, it can take any value. Now digital signal means if the amplitude of a signal can take only a finite number of pre-specified values only within a certain range of amplitude. So let us consider this situation. We have signal like this. This is horizontal line. These are horizontal lines. That means from 0 to say 0 to 1, a signal is with voltage 1. Voltage value is 1. From 1 to 2, the voltage value is say 2 volt. From 2 to 3, voltage value is again 1 volt. That means within a range of 2 to say 0, within this range, the signal can take either 1 volt or 2 volt. So it cannot take 1.5 volt. It cannot. So under this condition, we call this particular signal as digital signal. Now we have another classification of signal depending on its time value. That means the time axis. One is continuous, another is the discrete. Now, what is the meaning of continuous signal? If the signal exists at every time within a certain time interval, then the signal is called a continuous signal. Consider this signal, or here, or just this signal. This signal exists at this time, this signal exists at this time, this signal exists within time within these two periods of t1 and t2. The signal does exist, so it is a continuous signal. This is an example of continuous signal. Also, this one is example of continuous signal. That means this signal is digital and continuous signal, because it exists at every point of time. Now consider the situation of discrete signal. If we take the sample of this signal, the sample may look like this. Here the signal exists at that particular time, or at that particular time, or at that particular time, and the signal is not existing within this time interval. So within two samples the signal is 0 and signal exists at a particular time instant. These type of signals are called the discrete time signals. Now if the signal is taken from an analog signal, these samples are taken from an analog signal, then this signal will be discrete and analog. But if the samples are taken from this particular signal, then the samples may be like this. So here these two samples are of equal size, these two samples are of equal size, these two samples are equal size of 2 volt. That means this particular signal is a discrete time signal, but at the same time the signal is digital. We can divide the signal in another way. One is called the deterministic signal and random signal. Deterministic signal means we can completely specify this signal with the help of some equation. That means if we put the value of time, we will get the corresponding amplitude of the signal. There is another kind of signal that cannot be specified in this with the help of this type of simple equation, because if we specify the time for the random signal, we will get the amplitude value along with certain error. That means random signal cannot be completely specified by any equation. This is what we call random signal. So now let us recapitulate some older things. First, if we try to analyze the signal, we must differentiate different type of we must analyze different type of signals. So we must know what are the different type of signals. Now signal energy is defined in this way. If gt is the signal, then integration from minus infinity to plus infinity gt squared dt is the signal energy. Now if the energy of the signal is finite and average power is 0, then that particular signal is called the energy signal. Similarly, we define the power of the signal in this way: limit t tends to infinity 1 by t minus t by 2 to plus t by 2 gt squared dt. Generally, this type of signals, when this signal is periodic in nature, then we use to determine the corresponding power. So power signal must have an finite average power and infinite energy. So we have two type of signals, energy signal and power signal, and we can differentiate these two type of signals in this way. These are few signal operations. This is the time shifting operation. If gt is the signal, this is arbitrary signal, then gt minus t means it will be shifted, it will be delayed rather, it will be delayed by an amount t, and gt plus t means it will be advanced by an amount t. Next is the time scaling. If this is the signal from t1 to t2, gt is the signal, then G2t will be like this. It will be, instead of T1 it will be T1 by 2, instead of T2 it will be T2 by 2. Similarly, Gt by 2 will be, instead of T1 it will be 2T1, and instead of T2 it will be 2T2. This is what we call time scaling. Now time inversion implies that, as if we have a mirror in this y-axis, so the mirror image of this signal will be G minus T. So this section in the positive axis, positive time axis, will go to the negative time axis, and the negative time axis will go to the positive time axis. This is what we call the time inversion property. Now let us see some common type of signals. One is the unit step function. So unit step function ut can be written in this, can be drawn in this way. The value is 0 when time is negative, value is 1 when time is positive. So ut equal to 0 for negative time, ut equal to 1 for positive time. We have unit impulse function written as delta t equal to 0, and for t not equal to 0. That means the value of this function will be 0 everywhere except at t equal to 0. It must have this property minus infinity to plus infinity delta t dt equal to 1. So this is the representation of this delta function. This unit step function is also called the delta function. Next we have ramp function. So for negative time the value is 0, and for positive time the value is proportional to t. So it will going on increasing in this way. Now let us consider the orthogonality of the signal. If we have two signals x1t and x2t, then if within a certain period of time t1 to t2, x1t multiplied by complex conjugate of x2t dt is equal to 0, if this condition holds, then these two signals x1t and x2t are said to be orthogonal in nature. Now if we have two signals gt and zt, then the cross correlation function psi gz tau can be defined as integration minus infinity to plus infinity gt zt plus tau dt. Next we have autocorrelation function. These are actually known to you, we are just recapitulating it. Autocorrelation function, it tells us how a signal is identical to itself. So if gt is the signal, then gt multiplied by gt plus tau dt within a limit of minus infinity to plus infinity will give you this psi g tau. This is called the autocorrelation function. Now consider the Fourier series. Any periodic signal may be represented by an infinite series. So GPT is a signal that can be expressed as a0 plus summation n equal to 1 to infinity an cos n omega 0 t plus bn sin n omega 0 t within a limit of t1 to t1 plus t0, where omega 0 is 2 pi by tau t0. We can determine this coefficient a0, an and bn in this way. Now instead of using that particular type of representation, we can represent this Fourier series in slightly different way as well, like n equal to minus infinity to plus infinity cn exponential jn omega 0 t. So this is another way of writing the same Fourier series. This coefficient Cn can be defined in this way, and you can evaluate this Cn using this relation. These are also known to you. Now we will consider the Fourier transform. If xt is not a periodic signal, then we can, instead of expressing this xt in terms of Fourier series, we have to express in terms of Fourier transform. We can use Fourier transform if xt is time limited. So Fourier transform of xt written as x omega, x is written in capital, that can be defined in this way: minus infinity to plus infinity integration xt to the power minus j omega t dt. Now if x omega is given, then we can have inverse Fourier transform in this way: f inverse x omega equal to 1 by 2 pi minus infinity to plus infinity x omega e to the power j omega t d omega. And instead of using this omega notation, if we use df, then this 2 pi will not be there. Okay. Now if gt is a real function of t, then g omega and g minus omega are complex conjugate. That means g minus omega equal to g star omega. Now consider some common Fourier transform of some common functions like e to the power minus at ut. So g omega, gt is this, then corresponding g omega, you can use the previous notation of determination of Fourier transform, and the expression will be like this: g omega equal to this one. So we can divide this g omega into its magnitude part and the phase part. The corresponding plot is this, magnitude plot is this, and phase plot is this. Similarly, if we have a gate function gt, the value of gt is a, from minus tau by 2 to plus tau by 2, and 0 otherwise. So g omega can be determined as a tau sinc omega tau by 2, and the sinc function looks like this. So gate function is Fourier transform is sinc function. Now consider the Fourier transform of unit impulse delta t. Delta t is this. So taking the Fourier transform, we will get 1. So g omega is equal to 1 irrespective the value of omega. That means delta t contains all the frequency components of equal amount. Similarly, we can get inverse transform of delta omega, that is equal to 1 by 2 pi. So we can write 1 by 2 pi is Fourier transform is delta omega, or 1 Fourier transform of 1 is 2 pi delta omega. Inverse Fourier transform of delta omega minus omega 0, 1 by 2 pi to the power j omega 0 t. So e to the power j omega 0 t is Fourier transform of this function is 2 pi delta omega minus omega 0. Similarly, the Fourier transform of e to the power minus j omega t 0 is 2 pi delta omega plus omega 0. The Fourier transform of cos omega 0 t is determined as half of e to the power j omega 0 t plus, cos omega 0 t, the Fourier transform is pi into delta omega plus omega 0 plus delta omega minus omega 0. So this is the cosine function, and its spectrum, we have two spikes at frequency omega 0 and at frequency minus omega 0. This is the Fourier transform of signum function. Signum t equal to 1 for t greater than 0, minus 1 for t less than 0. And the Fourier transform is 2 by j omega. Now let us consider few common Fourier transform pairs that we are going to use very occasionally. So this one is delta t is Fourier transform is 1, cos omega 0 t is this, sin omega 0 t is this. The difference between cos and sin is basically there is a factor j, and this, instead of plus sign there will be negative sign. For signum function 2 by j omega. Then rectangular function, it is a sinc function. Similarly, for the sinc function, the Fourier transform is the rectangular function. So these are few common Fourier transform that we will use very often in this particular subject. Now consider some common properties of Fourier transform. The first property is the linearity property. So if we have two functions, g1t whose Fourier transform is g1 omega and g2t whose Fourier transform is g2 omega, then a1, if a1 and a2 are two constants, then a1 into g1t plus a2 into g2t, its Fourier transform will be a1 into g1 omega plus a2 into g2 omega. This is called the linearity property. Next is the duality or symmetric property. If gt, if it is a function, its Fourier transform is g omega, then capital G omega, then capital GT, the Fourier transform of this function will be 2 pi into small g minus omega. Next is the scaling property. If gt, its Fourier transform is g omega, then ga into t, its Fourier transform will be 1 by magnitude of a, g omega by a. Next one is the time shifting property. If Fourier transform of gt is g omega, then gt minus t0, this is the time shifting. This function gt minus t0, if we transfer it into Fourier domain, then it will be g omega e to the power minus j omega t0. That means shifting in time domain will produce a phase shift. E to the power j minus j omega t0 is the phase shift. It is the phase shift in the frequency domain. Next is the frequency shifting property, just like time shifting property. So if we change the phase in time domain, gt multiplied by e to the power j omega 0 t, that means we have changed the phase of the gt, then in Fourier domain that will be reflected by change of frequency, g omega minus omega 0. So there will be some change in frequency in the frequency domain. So these are few properties that we are going to use, or that we will use in this particular subject. Next is the convolution. The convolution process is used to determine the output from a system for a given input. So if we have two functions gt and wt, then the convolution is written as gt star wt, and the convolution integral is gt star wt equal to minus infinity to plus infinity integration g tau wt minus tau d tau. Now if the Fourier transform of g1t is this and Fourier transform of g2t is g2 omega, then the convolution of g1t and g2t, its Fourier transform will be g1 omega multiplied by g2 omega. This is what we call time convolution. Similarly, we have frequency convolution. Now if you want to prove it, we first take the Fourier transform of g1t convolution g2t. So this is the convolution integral, and we are taking the Fourier transform of it. Now what we are doing, we are taking out this g1 e to the power minus j omega t, we are taking inside it. Now the inner integral d tau and dt, this position has been changed. So inner integral is the Fourier transform of g2t minus tau. Fourier transform of g2t minus tau. That means g2 omega e to the power minus j omega tau, using the property of Fourier transform. So we can write g1 tau e to the power minus j omega tau g2 omega d tau. So here d tau is the variable, so omega is constant with respect to this integral, so we can take it outside. So we have g2 omega minus infinity plus infinity g1 tau e to the power minus j omega tau, which is nothing but g1 omega g2 omega. Now if g1 and g2 has a bandwidth of b1 and b2, then if we multiply these two signals, the bandwidth will be b1 plus b2. Now we will consider the Parseval's theorem for energy signals. Actually, Parseval's theorem enables us to determine the energy of a signal with the help of its Fourier transform. So if xt is the signal and its Fourier transform is x omega, then energy of the signal is defined as minus infinity to plus infinity integration x square t dt. Now this x square means x into x. Now xt can be written as inverse Fourier transform of x omega. That means 1 by 2 pi integration x omega e to the power j omega t d omega. So instead of writing this xt, we will use this expression. So putting this expression for the second x, we have this. Now if we alter the or interchange the order of integration, then we can write it as x omega, and in the inner integration we have xt e to the power j omega t dt, which is equal to x minus omega. So energy is 1 by 2 pi minus infinity to plus infinity x omega x minus omega d omega. Now for real signals, x minus omega equal to x star omega, where x star is the complex conjugate. So x omega x minus omega equal to x omega x star omega, that can be written as magnitude of x omega whole square. So energy of the signal is 1 by 2 pi minus infinity to plus infinity x square omega d omega. So instead of using d omega, we can write it in terms of df as well. So then if we write it in terms of df, then there will be no one, this 2 pi factor will not be there. So we can determine the energy of a signal, of the same signal, from its Fourier transform. This is what we call Parseval's theorem for energy signals. Now consider linear system. If superposition theorem holds for a system, we call it as linear system. So if yt can be written as some operation of a1 x1 t plus a2 x2 t, so if superposition theorem holds, then we can write it as a1 operation on x1 t plus a2 operation on x2 t. And a linear system can be modeled in this way. The impulse response ht and its Fourier transform is h omega. This h omega is the transfer function of this system. So if xt is the input signal, yt is the output signal, then we can write yt equal to xt convolution ht. In Fourier domain, we can write y omega equal to x omega into h omega. Now consider the distortionless transmission. A transmission is said to be distortionless if the input and the output have identical wave shape. That means there should not be change in wave shape. Wave shape must retain its original shape. But there may be some delay and there may be some change in scale. That means the amplitude may vary. So if xt is the input signal and yt is the output signal, then for a distortionless transmission, yt must be equal to some constant k xt minus td, where td is some kind of delay and k is a constant scaling factor. Now if this constant is multiplied with this xt, then there will be no distortion, because suppose k equal to 0.5, so amplitude of x will be halved. Now we can easily recover its amplitude by using an amplifier of gain 2. So if k is half and if we amplify this signal, then we will get our original amplitude. So it is very easy to get our original exact xt just by using an amplifier. Similarly, if there is some delay, that will not be considered as distortion, because delay will not change the shape of the wave. Now if we take the Fourier transform of this equation, it will be like this. There will be a term of e to the power minus j omega td. So x omega is this, and k into e to the power minus j omega td is written as h omega. So h omega is the transfer function of this system, which is distortionless in nature. Now if we divide this h omega into two sections, one is the magnitude part, another is the phase part, then magnitude part will be k and phase part will be minus omega td. So here the magnitude is plotted against omega and magnitude is k, so it is this horizontal line. This solid horizontal line is the magnitude response, and if we plot this theta h omega, the phase part, it will be this dotted line, which is proportional to omega, or minus omega rather. So for a distortionless system, we can say the magnitude response must be independent of frequency. Magnitude is constant means it must be independent of frequency, and phase response must be proportional to frequency. So this is the primary condition of having a distortionless system. So in this class we tried to understand the basics of communication, the basic block diagram of communication, what is the meaning of modulation. These are the basic things, and we tried to recapitulate some signal and system related issues without any derivations. So these are just a recapitulation class. From next day we will try to understand the basic modulation processes. Thank you.